Hello class. Today I want to pick up where we left off the other day in the classroom, and today's focus is going to be on atomic mass, moles, Avogadro's number, and the calculations involved with that. The last time we talked about chlorine as being the chemical symbol, and the atomic number being 17, which is the number of protons. And we talked about the atomic mass. We talked about that the atomic mass is relative to carbon-12, that carbon-12 weighs exactly 12 atomic mass units, and that all other atoms on the periodic table are relative to that. And we said that for chlorine, there would be different isotopes of chlorine, and the percent that they occur in nature, called abundance, we would multiply that percent by the mass of that particular isotope and add that together to get a weighted average. So that's what this slide is showing. It says atomic mass. We learned that all atoms of an element have the same mass. We learned that not all atoms of the same element have the same mass, that we have isotopes which have different numbers of neutrons. And so the more neutrons, the more that particular atom weighs. And the other part is that it is an average. It is a weighted average that and that's how we arrived to the atomic masses that are on the periodic table. All right. The equation we use, this looks like some fancy equation here. It says the atomic mass is equal to the summation of the fractional abundances of the isotopes times the mass of the isotopes. And what we said the other day is we know what the mass of the isotope is. So we have a mass, and then we multiply it by its fractional abundance. Like if it's 94%, that's 94 divided by 100. And then we hit equals and we get a number here. We do that for each isotope. Maybe there's only two isotopes, and the other isotope's mass times 6 out of 100, 6%, equals a number. We'd add those two numbers together and we get the average. So this isn't anything fancy that we haven't talked about before, but they show you a problem of how we're going to calculate the average atomic mass after this slide. Now this slide is called the mass spectrometry slide. You may be asking, how do we determine the mass, or be able to distinguish the mass between two different atoms, and those two atoms having the same chemical and physical properties, the only difference being the neutrons? Well, we have a machine that can do that. It's called a mass spectrometer. And the mass spectrometer is able to measure the differences in masses of two isotopes. What happens is we take the atoms, we put it in the machine. The machine adds a charge to the substance, and then we manipulate the charged particles through the machine, and it's able to separate the different massed objects. And here is an example of chlorine. When we take pure chlorine gas and we put it into a mass spectrometer, we get a spectrum, and we find out about 75% of the chlorine is isotope 35, and about 25% is isotope 37. And the mass spectrometer can distinguish between those two masses. Here's the machine. You put your sample in. This adds electrons to the sample. This sample is then it's in a beam, so it's all culminated. That's what these two pieces do here, is they keep the beam in a vertical angle. They also are electric. They're generally these are negatively charged. Your sample is negatively charged, these plates are positively charged, so it accelerates the charged substances down this tube. And when we reach this part of the tube, we know that one magnet is positive, one's negative, and so the thing that doesn't the charged particles that have the least amount of mass, they are bent by the magnetic field the most. Particles that are heavier, or the heaviest particles, they actually are bent the least, and they arrive on the detector in this spot. And you guys have experienced this. This is nothing more than you're driving down a road and you're in a car and you're coming into a turn, and if you're a light car, you can negotiate the turn because you don't have much mass. You can spin around the turn. But if you're driving a massive truck around that same turn, you couldn't make a tightest turn because the mass wants to go straight. So because of the forces of the turn, it's only going to turn slightly. And so that's what happens here. Light particles are, charged particles are bent considerably as they pass through the magnets. Heavy charged particles are not bent as much. And so we can separate very minute differences in mass between elements or compounds. Alright, so here's the problem that I want you to be able to do for the quiz and the test. It says that copper is 69.17%, copper 63, and it has, and it actually tells us the mass is a little less than 63. Now you go, why is that the case? Well, remember we talked about E equals mc squared. Elements heavier than carbon, some of the mass is converted to energy, nuclear energy, to hold the nucleus together. So that's why to 6 significant figures, this is a little less than 63 AMUs. For the rest, it's copper 65, and the mass of copper 65 is again a little less than 65 AMUs. But to 2 significant figures like we were doing yesterday, that would be fine. And they want you to find the copper's atomic mass. So what's given? Write that down. All right. Now, they don't give us the percentage of copper 65, but since there's only 2 isotopes, when you subtract 69.17 from 100, that will give us the percent abundance, or the just abundance of copper 65 in the environment. All right. So we're going to find the atomic mass. So what do? Well, here's your plan of action. Take the isotope masses, multiply it by the isotope fractions, and you'll get the average atomic mass. So here's the equation. Summation, which is a fancy word for addition. You add each fractional abundance of the isotope times its mass to the next isotope's fractional abundance and mass. When you add those together, you get a weighted average. So here's what it looks like. We take the 69.17, we divide by 100, that makes this a fractional form or a decimal form, multiply it by the mass of that isotope. Then here's the summation. That's what this is representing. The summation. So we add to that the fractional abundance of the other isotope, copper 65, and its mass. When we add these two numbers together, we get 63.5525. Now, we only have 4 significant figures in these numbers, so we're only going to know these to 4 significant figures. So to 4 significant figures, we get 63.55 AMUs. This is just like the problems we did yesterday. This one's a little bit more detailed. And you can check your answer by looking on the periodic table, and it looks fairly close to that number there. Back down the periodic table, it's 63.55 to 4 significant figures. Also, another thing I want you to be able to do here is by looking on the periodic table, you know it's 63.55. And if I tell you there's only 2 isotopes, copper 63 and copper 65, you should be able to tell me which isotope occurs the most in nature. And because the number is closer to 63 than 65, we know that isotope 63 is more abundant. All right, so we have another one here. This is gallium-69 with a mass of 68.9256 AMUs and abundance of 60.11%. And we have gallium-71, which is 70.9247 AMUs, and the abundance is 39.89%. Again, if you add these two percentages together, you will have 100%. It says calculate the atomic mass of gallium. All right, so we set up the problem. You write down what's given. Make sure that you use the right percentage with the right AMUs. And again, a little less than 69 AMUs. Because of the mass converted to energy. Do the same thing for gallium-71. All right, and what we're going to find is the average atomic mass, or we just say atomic mass in AMUs. Same conceptual framework, same equation, summation, and here it is. It's the percentage converted to decimal form times the mass of the first isotope plus the percentage of the second isotope converted to decimal form times its mass. When we add these together, we get this number. Notice they make a note there that they know where your significant figure should lie. So that's why they rounded this off to 69.72. And again, you can check your answer. Again, 68.9 is pretty close to 69. That one must occur more frequently than gallium-71. All right. I can see I'm about out of time on this particular lecture, so we're going to stop here, and I will pick up on the next lecture on the actual calculations dealing with moles. I hope this helps. Thank you.